In this video, we're going to talk about operations that we can perform on or with geometric vectors. So just like numbers, we can add and subtract vectors. So we can add, we can subtract, or we can multiply, and we can divide. And let's take a look at what that actually looks like. And to do that, we're going to start by looking at addition. So what kind of problems will we use this for? Let's take a look at an example. Adding vectors. Consider a boat that is being pulled in two directions. Where does it actually go? So if we just had this single force vector here, so this tugboat pulling the big boat, it would just go straight to the right, or in many cases we would say due east. But there's another boat pulling at an angle here. So how do I add up forces together? I can't just add the magnitude. Remember that vectors consist of two components, the magnitude and the direction. So this gets a little more complicated, but it is actually similar to problems that we've seen before. In order to do this, we're going to sketch each vector. So we're going to sketch F2, and at the tip of that vector, we're going to draw the second vector by drawing its tail. So it's going to look something like. All right, so in order to add vectors, we draw them tip to tail, and then we have a resultant vector, and that's going to be the sum of them. So if I start at the start and end at the end, my new vector here is my resultant vector, and that's our answer. What direction will the boat go in? It will go this way, and we could even, if we wanted, copy that over. And so the boat's going to go in this direction. So that's vector addition. But that's just a overall conceptual idea. How do we actually get the magnitude? How do we actually get the direction? Let's keep working and learn a little bit more about that. And this is called, before we move on, this is called the triangle method. And honestly, this is the method that I prefer. And your physics teacher will probably teach you this method as well. But there is another method called parallelogram method, and we'll get to that in a moment. All right, so just to kind of restate what we said, but in writing, adding vectors, consider a boat that is being pulled in two directions. Where does it actually go? When I add up those vectors, what we get is the resultant vector. So that's a key word, a new term that we want to know. And this is called, when we add these together, vector addition. So we add two or more vectors together. We get an overall vector that represents the same thing, and that's our resultant vector. And the two different methods that I mentioned, we did the triangle method first. If we do this method, and you'll notice this one's a little bit different here, I have the two vectors for my force vectors, so the one tugboat pulling this way and the one pulling that way, but instead of arranging them tail to tip, I arrange them tail to tail, and that's what's going on here. Tail to tail. So we can see the difference here. Instead of going over and then up, we're starting them both at the same source, and then we draw a parallelogram. So basically, we draw our original vectors here, and then we copy them over here, and then we connect from one diagonal to the other of the parallelogram. Honestly, I don't prefer this method, but we're still going to take a look at it. And we can see here, and I'll zoom in a little bit so we can see that a little more clearly, that with our parallelogram method, we have our original vector, or our original vectors. We have the angle between them. We've completed the parallelogram by kind of recopying them over. Basically, you're still kind of drawing tail to tip and tail to tip. Our original starting point, our end starting point, and our diagonal, our end starting point. Our original starting point and our new end point is right here. So the vector OG is equal to the resultant vector we got before, which is force vector 1 plus force vector 2. So we're going to get the same answer either way. We've just drawn a different shape to get there. I like the triangle, less drawing. It just makes more sense to me. But parallelogram method is also a valid method. All right. Let's take a look at a little more detail of the parallelogram law. So once again, you're arranging these tail to tail. Vector A and vector B, or in our specific case, it was vector F2 and F1, but in the general case, vector A and vector B, we arrange them like this. We can label our points A, B, and C. And now we can draw a triangle. We know quite a bit of information already. We know this is theta. We know from our sketch this is going to be our resultant vector, and we can figure out our missing angle here from just 180 minus theta. And so we can see that vector A plus vector B is equal to the vector AB plus the vector BD. So basically, it's basically triangle method again. And the resultant is the one that starts at the start and ends at the end, and that's vector AD. Oops. And we've already discussed the triangle law, but let's take a look at it in general form again. We looked at it for a specific case, so let's talk about it generally. The triangle law for adding two vectors. Take our two vectors, our original A vector and our original B vector, and place them tail to tip. And then for the resultant, for the sum of those vectors, start where we started, start at the tip, or tail, start at the tail of the first vector, go straight to the tip of the final vector, and this A plus B vector here is our resultant. Like we said here, place tail to tip. And the resultant vector starts at the very beginning and ends at the very end. And I'm going to keep saying that because I know that students have trouble grasping that the first few times through. Basically, the way I always think of it is start at the start and end at the end. And we can see in this more complicated example here, where we're adding together four different vectors. The question is, what is the resultant vector here? And you're like, well, shoot, before I just kind of went like this, but then what do I do with this stuff now? Start at the start and end at the end. Where is the tail of this set of vectors? It's right here. Where's the tip going to be? Right here. So there we go. We've just added four vectors all together all at once, and we have a resultant, and we're already ready to go on. We haven't done any calculations yet. We just want to get the concept of what does vector addition look like, how do I sketch it, things like that. Let's take a look at an example, and we'll start doing some calculations now. An airplane heads due east at a speed of 300 kilometers per hour and meets a wind from the west. So read carefully, from the west. I'm going to highlight that immediately. At 100 kilometers per hour. What is the resultant velocity of the airplane relative to the ground? Oops. Let's try that again. Trying out some new technological tools. All right, there we go. Let's keep going. So we're going to sketch each of our vectors. So first of all, what do we know about the wind? We know the wind is coming from the west. So our wind is coming from the west at 100 kilometers an hour. So we'll show that coming from the west right here. And we can label this is like our wind vector and 100 kilometers per hour. And the plane is heading due south, so straight down. at 300 kilometers an hour. And I didn't really draw this to scale. If we were in physics class, or we wanted to measure this manually with a ruler or something, which we could do, we could make a scale drawing, the vector lengths would matter. But just like most of the triangles we draw in class, we just try to draw an approximate shape and make sure our labels are correct. So this is our plane vector. And how are we going to do our vector addition? Well, I'm going to redraw this off to the side. Like I said, I like the triangle method. So we're going to have the wind, we're going to have the plane, and we are going to have our resultant vector, which will tell us which direction the plane is actually going in. So we're doing W vector plus VP vector equals our resultant vector. All right, and we have a triangle. Now let's label it. See if I can tidy this up a little bit. I'll just redraw that a little more neatly. All right, it's still starting at the start and ending at the end. It's just a little sloppy. All right, we have a triangle. What do we know about this triangle? Well, I know this is a 90-degree angle. I know the length of my wind vector right here is 100. I know the length of my plane vector. It is 300 kilometers an hour. So we can actually find our missing side length right away. We can find what is the speed the plane is traveling at, so the magnitude of that velocity vector, and let's find that. We'll just use Pythagorean theorem. C squared equals a squared plus b squared, or in our case, the magnitude of r squared is a squared plus b squared, so 100 squared plus 300 squared. And that'll give us, because I don't really need a calculator for this, just have it. All right, 100 squared. Oops. It's going to give us 1,000. No, it's not. It'll give us 10,000 plus 300 squared. It's going to give us 90,000. We're going to add those together, and we'll get 100,000. We take our square root, and we get 316.2. Magnitude of the r vector squared, took the square root, so the magnitude of the r vector is 316.2. So we know how fast the plane is going, kilometers per hour. Now we just need to find the direction. We can measure the direction relative to any compass point. So I'm going to find our angle theta right here. I'll switch to a different color here. So we're going to be measuring relative to east. We're going to be measuring relative to east. So let's find our angle. How am I going to find my angle? Well, it's a right angle triangle. I can just use my trig ratios. Let's label our sides: hypotenuse, opposite, adjacent. Technically, we know all the sides. I know the length of my hypotenuse, so I could use any trig ratio, but I prefer to use the values given in the question, because if I rounded, if I made some kind of calculation error with my 316, then I'll be in trouble. So I'm going to stick with the values they originally gave me, so I know the opposite and the adjacent. So I'm going to use tan to solve for this one. Running out of room a little bit here. I think we can squish it in still. So tan theta equals O over A. I usually find it helpful to write the original formula before I plug in my values. I'm going to rearrange right away just to save time here. So theta equals tan inverse of my opposite side was 300. My adjacent side was 100. So tan inverse of 300 over 100, or in other words, tan inverse of 3, is going to be 71.6. All right, and that's enough information. What do we need for a vector? We need to know the magnitude, and we need to know the direction. I know the magnitude of that side of my triangle, or my vector. I know the direction, so let's state it. So let's go back, make sure we've answered the question. What is the resultant velocity of the airplane relative to the ground? Therefore, the resultant velocity is 316.2 kilometers per hour, and our direction is east, 71.6 degrees south. So basically we're starting in the east and then rotating around. Or normally we want to measure from the closest compass point. I just wanted to show that we can think about it in two different ways. So let's also restate our final answer here. Same thing, I don't have room to write this all, but therefore the resultant velocity is 316.2 kilometers per hour. And our direction, we're just going to measure from the other compass point from south and swing that way, is south. And then 90 minus 71.6 gives us 18.4 degrees east. Congratulations, we just added a vector. Actually, we added two vectors, so we've now practiced vector addition. Let's keep moving on. All right, let's try a different example. Consider two math students pulling on a sled. One student pulls with a force of 10 newtons, so that's the magnitude of that one, in the direction north, 33 degrees east. So we can sketch that. We have our plane, so we can sketch it on there. So one of them is going to be blue, so let's match with the blue. So 33 north, 33 degrees east. So to start at the north, rotate 33 degrees east. And I don't like that line. Let's redo that. All right, north 33 degrees east. This is our A vector. And our B vector is east 15 degrees north. So mostly east, but a little bit north. There's our B vector. All right, and then basically we can do our parallelogram method, where we would basically draw a copy of the B vector up there and sketch a copy of the A vector there. And we're finding our resultant vector. So it starts at the start and ends at the end, or with our parallelogram, it goes through the middle. So we're trying to find this resultant vector right here. So let's actually do that. We have part of the diagram drawn here already for us. So everything's nicely sketched. We have our triangle. So now we need to use what we know about trigonometry to find our missing angles and any side lengths that we know. So let's start with the side lengths because they're nice and easy. Do we know this? Do we know the length of vector A? Yes, we do. It was said in the question that one student, the one pulling north 30 degrees east, so that's our A vector, has a force of 10 newtons. So let's label that. So this has a side length of 10. And the B vector, said up here in the question, the other student was pulling with a force of 7 newtons. So let's label that with the 7. And I almost know enough to solve, but I don't actually know any of the interior angles. I only know a couple exterior angles. So thinking what we know about alternate angles and corresponding angles and things like that, we can put a few pieces of the puzzle together. So if this is 33 degrees, then based on what we know about, like I said, alternate angles and stuff, I also know this angle right here. So I think that's alternate angles, or sometimes we call it Z angles. So if that's 33, this is also 33 degrees. And we also know, right beside it, that this part right here is a 90-degree angle, and I know the other part here is a 15-degree angle. So we can just add those all up. I can find that angle right there. So this total angle here is going to be, and we'll call that our theta. Just don't have room to write it in there. So theta is going to be equal to 33 plus 90 plus 15, which is going to give us an angle of 138 degrees. So our angle theta here is 138 degrees. And now we have enough information. I have two side lengths and a contained interior angle. So let's use our cosine law to solve. I want to find the length of my resultant vector. So I'm just finding the side of a triangle, and I'm going to use my cosine law. So whether you call it side A, B, or C doesn't really matter. I prefer to use C as my unknown. So C squared is equal to A squared, so 10 squared, plus B squared minus 2AB cosine, cosine C, and that's that 138 we just found. All right, let's solve. I'm not going to show all my work, but basically, so 10 squared plus 7 squared minus 2 times 7 times 10 times cos 138. And make sure your calculator is in degree mode, no radians yet. And c squared is going to equal about 253.04. We need this actual c value though, so we'll take that square root. And we're going to get 15.9. And our units are going to be newtons. All right, so far so good. I know the magnitude of that vector. I know the side length. Oopsie. Now I just need to figure out the direction. How are we going to find the direction? Well, we have enough information that we can just use our sine law. So I'm going to relabel my triangle here. This has a length of 15.9. So now I know corresponding sides and corresponding angles. And basically, we're going to find this missing angle here. We'll just call it beta. So let's use, and I'll move our other writing here out of the way. Let's try that again. We'll just slide that up to give us room to work. All right, let's find our angle. So to find angle beta, we're going to use our sine law. So sine beta over opposite side is 7 equals sine 138 over 15.9. Once again, I'm not going to show all the rearranging, partly for the sake of time, partly for the sake of I don't have a lot of room on the page. Hoping to get an Apple Pencil to make this a little easier to write on, but for today we'll do the best we can. So rearranging, sine beta is going to be 7 times sine 138 divided by 15.9, and we find sine inverse of that value, and we get 17.2. Sorry, 17.1. And that's kind of all we need. Yeah, so depending how we should measure from the closest compass point though. So 17, 30, 40. Yeah, that's fine. So we know this angle here, focusing back over here. So measuring from our nearest compass point, which is north, and rotating all the way around, it's going to be 33 degrees we already had, plus the 17.1 we just found. So let's call this angle, I don't know. We'll find the angle though. I think it's gamma. Is gamma the one that looks like this? We'll find our new angle. So we already had 33 degrees plus our 17.1 degrees gives us 50.1 degrees. So let's state our final answer. We know the length, we know the direction. Therefore, and what were we trying to find? The total force on the sled. Therefore, the force on the sled is 15.9 newtons in the direction of north 50 degrees east. Or we could state it the other way, 15.9 newtons east, 40 degrees north. Same thing, it's just relative, it just depends where we're measuring from. All right, we have successfully done a couple different examples of vector addition. Let's see what's next. And here's our overall steps. So how to calculate the resultant vector. Let's just make sure we understand the process. So draw your diagram using either the parallelogram law or the triangle law. Use the diagram to find the interior angle opposite the resultant. That's what we just did. Use the given magnitudes and angles to find the magnitude of the resultant vector using cosine law. Just did that. And to find the direction of the resultant, use sine law to find the interior angle, and then use your diagram to find the direction of the resultant. And we just did that. And yeah, we want to make sure of the direction that the resultant vector is going. So it's starting down here. Sorry, you can't see my presses on the screen, so I'm going to use the highlighter for a moment. It's starting down here and ending up here. So it's heading, like northeast. It's not heading back the other way. Be careful watching the direction, because if the arrow and the tip and the tail were reversed, then we'd be heading in a more southwesterly direction. So watch out. Make sure that you're measuring the right way. All right, we have successfully added some vectors. What else can we do with vectors besides addition? Let's see.